Swayam Prabha. Digital India. Educated India.
Let us start this lecture with a thought process from Swami Vivekananda, who is one of the proponent of the spirituality in the entire world, and he says, "Arise and awake, stop not till goal is reached." This is a very great statement for all of us, because we sometimes get bogged down with the problems. He says that one has to really try to achieve certain goal, and for the emancipation of the self and also the mankind. Let us now recall what we learnt in the last lecture. In the last lecture, we basically looked at the thrust coefficient and how one can really optimize it and get the maximum thrust coefficient, and what are the problem associated with. And we also looked at the variation of thrust coefficient with area ratio for with the variation of also the PT2 by PA for a particular gamma that is equal to 1.2. And we can have similar plots for various other gammas, like gamma is equal to 1.4, maybe 1.25 or any other things, depending on the kind of propellants we will be using. But the plots will be similar in nature, but the number may be different. So today we will be looking at another very important parameter that is already we have defined, and that is characteristics velocity. It is defined as basically ratio of PT2 by A star divided by the mass flow rate of propellant, and this characteristic velocity is denoted by C star. Basically this is your characteristics velocity, and this is you can really obtain from the measurement values of the chamber pressure, that is PT2, and the throat area under choked condition, and mass flow rate of the propellant. All these can be measured very easily, so you can get a characteristic velocity. Now we will try to relate this characteristic velocity in terms of other parameters like your temperature and other things, so that we can evaluate it from the theory itself. So for that we will have to get from the isentropic flow the mass flow rate corresponding to the choked condition, that already we have discussed earlier. The expression for choked mass flow rate of the propellant through the rocket nozzle will be equal to PT2 A star root over gamma divided by R TT2, and of course to the 2 by gamma plus 1 power to the gamma plus 1 divided by 2 gamma minus 1. Already we know this expression. What we will be doing that now, basically we can substitute this equation 13 in 16. Then we will get C star is equal to basically PT2 by A star divided by PT2 A star root over gamma divided by root over R TT2. Into 2 by gamma plus 1 power to the gamma plus 1 to gamma minus 1, right. So this, if you look at this, will cancel it out. I can get basically C star as equal to, I can say this will be gamma plus 1 divided by 2 power t gamma plus 1 divided by 2 gamma minus 1 and 1 divided by root over gamma into this root over r t t 2. So, if you look at, I can get an expression by that, and here root over of 1 over gamma plus 1 divided by 2 and power to gamma plus 1 divided by gamma minus 1 r t 2, and r, instead of gas constant we are writing this is universal gas constant divided by molecular weight. Keep in mind that this particular terms, we can say that is basically, I can write down this term as, this is basically gamma. This term I can call it basically 1 over by gamma, and I can write down this is r t t 2 divided by gamma. Is equal to, this is 1 over by gamma. What it really indicates? It indicates the characteristics velocity is basically the function of the temperature, and the higher the chamber temperature, the higher will be the characteristics velocity, and lower will be the molecular weight. If you look at, the lower is the molecular weight, the C star will be higher, and if this temperature is higher, the C star also will be higher per particular gamma. And that is the reason why one can have some propellants with lower molecular weight, and that can be achieved when you can add some constituents like hydrogen so that the molecular weight can be reduced. And of course, the temperature having certain limitation, because you cannot go beyond certain temperature at a particular pressure, because of fact that there will be dissociation of the species which will be occurring. As a result, temperature will be dropping down. Generally, the combustion temperature in the range of 2800 to 3500 Kelvin are being used for the propellant. And beside this, you can also look at this C star is equal to PT2 by S star by MP. What it says, that it also indicates that capacity of the propellant to produce the certain chamber pressure for a certain mass flux of the propellant, that is m dot p by throat area. And of course, interestingly, you can look at that, it says that what is the extent of combustion one can take place in the thrust chamber. Therefore, this is the important parameter for the finding out the performance of the combustion in the thrust chamber, and that we will see that how does the C star will be varying with the temperature and also for a particular gamma in the subsequently. But let us now look at as this characteristics velocity is basically indicates the performance of a thrust chamber, and similarly we have also derived earlier the thrust coefficient, which is an indicator of the performance in the rocket nozzle. So, now using that both, we can try to find out an expression of the specific impulse in terms of the thrust coefficient and the characteristics velocity. So, if you look at the Cf, we know by definition F by PT2 by S star, which is a function from this we can derive that thrust is equal to Cf PT2 S star, right. And we know from here that is basically we can write down this is Cf C star m dot p, because PT2 if you look at from this equation 16, from this equation 16, so we can write down that PT2 A star is nothing but C star m dot P. And we know that that means by knowing the thrust coefficient, by knowing the characteristic velocity, by knowing the propellant flow rate of a rocket engine, we can find out what will be the thrust. So, therefore, we can write down as F is equal to m dot P C F and C star. And we know this ISP specific impulse is basically F divided by m dot P into G. If I say this F is equal to, basically you can write down m dot P C F C star. So, this is cancel it out, and you can very happily write down ISP is equal to C F C star divided by G. And this is a very simple expression. You can see that if I can know the CF and if I can know the C star, then I can get very easily ISP. And keep in mind that the CF and C star at the sea level particularly it can be measured very easily by knowing this total pressure, chamber throat areas, mass flow rate of propellants, and also the thrust, so that we can get this value CF and C star. And as I told earlier that this thrust coefficient indicates the performance of a nozzle, and the C star indicates the performance of a combustion chamber or the thrust chamber. So, one way of obtaining the CF value is basically from the experimental, and which will be the actual one, and another way of calculating the CF from the theoretical analysis by making lot of assumptions what we have done, considering the flow to be isentropic, one dimensional and steady, and all those assumptions we have already made. So, that to have this thing, how much it is different, we need to define the certain coefficients, like for example, like we can say the combustion efficiency. When we are considering the characteristic velocity, combustion efficiency is defined as the ratio of actual characteristic velocity divided by ideal characteristic velocity. Ideal characteristic velocity you can obtain from the theoretical values, that is from the equation 17. Basically, these values will be varying something 0.95 to 0.99. Generally, people always try to manage to get something 0.99. And in the similar way, we can also define the thrust coefficient, that is effectiveness of the thrust coefficient. We call it thrust effectiveness, is basically ratio of CF actual divided by CF ideal, and these values also will be varying something around 0.92 to 0.98 or sometimes kind of things. These values people can get very easily. And keep in mind that the CF ideal can be obtained theoretically. We have already derived expression for that earlier, and CF actually you can get from experimental data. So, let us now look at this, how does this CF vary with the TT2 and for a fixed values of specific heat ratio and molecular weight, because if you recall that we get CF is a function of TT2 m bar, what I am saying, molecular weight and gamma. And here we have plotted the characteristics velocity C star versus the chamber temperature, and you can see that it is increasing with the chamber temperature or the, and naturally one will be tempted to go for a higher characteristics velocity to obtain the higher specific impulse. However, I told you there is a limitation, one cannot really go beyond the 3500 Kelvin because of dissociation of species will occur, and then it can come down the temperature. Other thing is that heat losses will be much higher because the material one has to use and management of the cooling of the combustion chamber, and the rocket nozzle will be difficult. And beside this, the thrust chamber is subjected to high pressure and high temperature. Therefore, the material is also one constant. And you can notice another thing is that with gamma there is a difference, and that means you will get a little increased characteristic velocity when gamma is equal to 1.4, and we have seen earlier that you will get higher thrust coefficient for a lower gamma, and of course this can be compensated with each other. So, you can see that this is very important aspect. One has to look at what characteristic velocity one has to use. So, let us now summarize the thrust coefficient and specific impulse, and like make some few remarks. It is more desirable to run the rocket engine under expanded rather than over expanded one, because of fact that we have seen already when the nozzle is over expanded, the flow is quite complex, and the shock being formed, and the losses will be exorbitant, and then also the flow separation is likely to occur more, and that must be avoided. However, one cannot really avoid the under expansion and or the over expansion, or one cannot, in other words, one cannot operate the rocket nozzle at a fully expanded all the time, because the ambient pressure will be changing along with altitude. And as I told earlier, that we need to use a shorter nozzle for reduced weight and size. Therefore, I told you that the pressure ratio of 33.3 is basically the optimum one what is being preferred for design. So, the increasing pressure ratio improves the performance here, but the improvement diminishes above the 33.3 of the pressure ratio, of 33.3. So, therefore, its operation design is limited to that, unless otherwise a high pressure ratio, that is PT2 by PA, is called for. The large nozzle exit area is required at high pressure ratios. Implication particularly that when you are operating at a deep space, for the space applications, one has to use that. And high temperature value is desirable for high specific impulse, because of fact that we can get a higher values of C star, but it incurs the problem with the heat transfer and also the dissociation of combustion products, and which is the practical limit of the temperature is around something 2750 to 3500 Kelvin, depending on the propellant. And low values of molecular weight is more desirable, because of we can get the higher specific thrust, and of course, for that one has to go for the hydrogen based propellants, and so that the molecular weight of the gaseous product will be lower. And low values of gamma is desirable, as I told earlier, because you can get the higher specific thrust, but however it is not that easy to get. So, therefore, generally the rocket propellant values vary something 1.2 to 1.3 kind of things, and for maybe non-chemical rockets one can really get the different values of gamma, or low values one can design, particularly gaseous kind of rocket engines. The characteristics velocity is dependent on the chamber temperature, gamma, and independent of the chamber pressure, that we have already seen, and you should keep that in mind. And C star and CF value are the performance parameter for combustion chamber and nozzle respectively, that we have discussed. So, by this these two parameters which really separates the performance, and so that we can look at it, and we have also defined certain parameters like your combustion efficiency and thrust coefficients or thrust effectiveness, so that which can really characterize how good the combustion in the thrust chamber by the combustion efficiency, and also the thrust effectiveness can tell us how good is the expansion in the nozzle, so that the thrust is produced. Let us consider an example, so that some of the points whatever we have discussed, it can be clarified, and that example is, in a rocket engine, hot gas at 2500 Kelvin and chamber pressure of 10 megapascal is expanded fully in a conversion diversion nozzle with a throat area of 0.15 meter square to the ambient pressure at sea level, that means altitude is 0, to produce the thrust, and determine the exit velocity, characteristic velocity star, and maximum thrust coefficient, the maximum CF, and the thrust and specific impulse. And you can take molecular weight 25 kg per kilomole and specific heat ratio gamma is equal to 1.25. So, if you look at given, that is T2 is equal to Tc is 2500 Kelvin, and we are having PT2 is 10 megapascal, and you are having throat area is equal to the choke condition 0.15 meter square, and it is at the sea level, altitude is equal to 0, and PA you can say 101325 Pascal. So, these are the data is given, and then we will have to find basically characteristics velocity, CF maximum, and thrust, and you will have to get ISP. So, we will have to assume the flow in the nozzle to be ideal, and we can determine the exit velocity as VE is 2 gamma RU TT2 divided by gamma minus 1 molecular weight into PE by PT2. So, if you look at in this case, the TT2 is given, this molecular weight is given, gamma is given, PE is given, PT2 is given. So, you can just substitute those values whatever we are having. Keep in mind that we are taking this approximately as 0.1 megapascal, and then when you substitute these values, you will get is VE 2367 meter per second. That is the exit velocity from the nozzle under this, of course, ideal condition or ideal. Similarly, we can determine the characteristics velocity C star, and gamma is given here in this expression, T2 is given. So, we will substitute these values, and you will get something 1385.59 meter per second. So, if you look at this is the important point, that is of course, in this example C star is not really much, but it is good enough to have a thrust. We will see now how much what is the maximum CF values. The ideal maximum thrust coefficient can be obtained, particularly when the nozzle is fully expanded. That means PE is equal to PA, right. This is your fully expanded nozzle. So, you will get these values because we know this gamma, we know P and PT, we can substitute these values and get very easily, and that happens to be CF maximum is 1.615. Hence, the specific impulse can be obtained very easily because already we got this CF and we got the C star, and that can be very easily you get, and because as the ISP is equal to C star CF divided by G. So, that happens to be 228.16 seconds because all these are known to us, already we have calculated. So, similarly, we can determine the thrust produced by this rocket engine because we know that by definition CF maximum is equal to F by PT2 by PA. So, this CF naught is known and PT2 is known, A star is known. So, you will find this thrust is being produced by to be very, by this rocket engine is quite high, 2.42 mega Newton. This is basically mega Newtons we are putting. So, you can look at that. By this one can really calculate very easily these values from the theoretical point of view, and if you want to find out the combustion efficiency or the thrust effectiveness, you need to know the measured values, so that we can find out. Thank you very much.